All right, my calc babies, we are finally into chapter 4, and we're going to switch gears a little bit. The second major topic of calculus is that of integration. And let me indulge me for a second. If you are a mathematician, say, and you come to me with this new operation that you've created, right? Some new operator. I tell you what, let's just say it's the idea of a plus symbol, adding, or the idea of multiplication. Now, my first question I'm going to ask is, okay, this is neat, but how do I get back? In other words, what is the inverse of your new operator, right? So don't tell me about addition unless you also have subtraction, or don't tell me about multiplication unless we also have division. And likewise, I don't really want to know about derivatives unless we also have integration. And because we want to be able to go forward or backwards. So we now turn our studies to the inverse of the derivative, which we call antiderivatives. Now, let me pose a question. So assume I said that the derivative of something is 3x squared. What is that something? Well, maybe those of you that are fairly good with arithmetic, mental arithmetic, maybe you might say, oh, that's easy, professor. The derivative of x cubed is 3x squared. To which I might say, well, wait a minute, hold on. How do you know that? Isn't the derivative of x cubed plus 1? Isn't that also 3x squared? What about x cubed plus 2? Isn't that also 3x squared? So how were you able to determine that it was simply the derivative of x cubed when there's a whole family, a whole infinite amount of potential functions that you took the derivative of? So more to say about that in just a second. But the general flow of this course has been from some f of x to some f prime of x, right? So you had a function to which you took the derivative of and ended up with f prime of x. Now we turn our attention to going from the derivative back to the original function. Only the notation is going to change a little bit, and we wouldn't have to do what this new notation, but it is the standard notation, and I want you to practice it. So the f of x for our purposes, right, from the section chapters 2, chapters 3, f has always been the original function. And f prime is the result, the derivative of the original function. But can you agree that if we're going to go backwards, then our original function is going to be the derivative, right? So that can be slightly confusing to some students because henceforward, lowercase f of x is going to be the derivative. So, and then when we find the result, the original function that we took the derivative of, right? When we go backwards, we're going to use uppercase f of x. And that's going to represent the antiderivative. So using the previous problem, we would say that the 3x squared is the derivative And now, note the use of language here. The x cubed is an antiderivative, right? And I chose this indefinite article here, an versus the, because it is one of, x cubed is one of many antiderivatives. In fact, any x cubed plus a constant, if you take the derivative of a constant as 0, so any x cubed plus c would have worked in this case. So since we don't know what the value of c was, then this is the family of antiderivatives. If you leave off plus c, in my mind you're lying to me, because the way I interpret you forgetting to put a plus c, the way I interpret that is you're telling me that c is equal to 0, of which you possibly could not know that from the information that was given. So, all right, so we have, all we have to know is, let's go ahead and use the f and capital F. So lowercase f of x, that's the derivative. That's what you're going to start with now. And we're going to work our way backwards to capital F of x, which is our antiderivatives. Okay? And now let me see how much space I have here. Let me talk a little bit about the notation that we're going to use for antiderivatives. So, okay. So the idea is that, I tell you what, we'll start, I think it'll be easier if we just simply start with something we already know, right? So if we start with dy dx is equal to f prime of x. Now, will you allow me to erase that prime symbol, since henceforward lowercase f is now the derivative, right? Since we're now going to call lowercase f the derivative because that's what you're going to start with, the starting function, will you allow me to erase this prime symbol? Not that I have to. It's just to keep my notation clean. Okay. Well, if you think about it, we can, using that, like when we were talking about differentials and that Leibniz notation of derivatives, we can treat dy dx as, for our purposes, a fraction, to which we can bring the dx to the right side of the equation, right? That was the point of the previous section. So I can rewrite this as dy is equal to f of x dx. With me so far, right? Not bad. Now, the symbol what we use when taking antiderivatives, it looks like an elongated S. It looks like this, right? And there's a little bit of history here of why that notation is chosen, but can you agree with me that, well, let's start with if I take your age and multiply by 2, then divide by 2, I'm right back to your age. And if I take the square root and square it, I've undone that operation. Then will you agree with me that so this is the integral, right? This is how we do, this is the integral. I'll give it a name in just a second. And I'll give all of these a name in just a second. So, but this is how you find the notation for finding antiderivatives. So this is how we undo derivatives. So then you would have to agree with me that if I integrate a derivative, that would be like if I square a square root. What would you be left with? Well, I mean, if you integrate the derivative, you would just be left with y. But I cannot just integrate the left side of the equation, right? We have properties, rules of equality that we gotta, so I have to integrate the right side as well. And so what we have is the integration of, now remember, f is now the derivative. The integration of a derivative with respect to some variable is going to be equal to y. Now, the only case and the only difference is I'm going to use right here, I'm going to use a capital F. The last thing I got to do is, and what you're going to see more of, is you're always going to have plus c, because if you don't have plus c, then you actually say, or telling me you know what c is, and you don't know what c is just by taking the antiderivative. Okay, so let's take a look at the very first question, right? So example 1, and then I'm gonna rewrite that that formula that I just wrote there just a second ago, and I'm going to tell you the name of each one of those parts. But right now, let's go to a question. So, how do you solve a differential equation? Right. So, for many of you, if you have thoughts and hopes and ambitions of becoming an engineer, then probably one of the last math courses that you'll take is a course on differential equations. You may even take it with me. Let me tell you right now, college is full of a lot of almost engineers. That is not a lie, and that's not to. And I'm not trying to take anything away from your dream. I'm simply trying to tell you that if you don't take your dream seriously, you will be another almost engineer. Math is a contact sport. It is a hands-on sport, and it will serve as an eliminator to the things that you want to do. And well, I don't want to, I love you, but you better take your stuff seriously, because the amount of students in my differential equations class is minimal compared to the amount of students in my Calculus 1 class, even though every single one of them had the same dream. And then unfortunately, some took my advice seriously, some did not. All right, but we'll see. Maybe you are going to be the one that makes it. Ready? So a differential equation is quite simply, and for this problem, is just an equation that has a derivative in it. That's it. So this is what we would call a first order differential equation. This is the equation. I'll use their notation. Y prime is equal to 2. Now, if you want to find the general solution of a differential equation, I'm going to highlight general solution for just a second, but let's go ahead and solve the question right now. So I haven't given you a formal way of how you take antiderivatives, but can you agree with me that obviously the derivative of something, that's what we're looking for, is equal to 2. And I think we can agree that for sure that something, I'll use y instead of a capital F, okay? Just because I want to mirror their notation. So if y prime is 2, then y must have been what? Must have been 2x plus, because we don't know if there was a constant added to it. So 2x plus c. This is the solution to this differential equation. And now the geometry of what that plus c means. So look, do you see all these lines running parallel to each other? Each of those represents a different value of c. C is 0, C is 2, C is negative 1. Since we don't know the value of C yet, then we have a whole family of potential curves. Okay? Each of these is 2x plus some constant. Okay, and now let me go ahead and rewrite this this notation that I was talking about just a second ago. So when you're the notation that we're going to use, so I'll read theorem. Actually, let me not forget, because let me not forget to talk about what they mean by general solution. Okay, so just really quickly, the general solution, to make it really simple, just means you still have a constant C in your answer. Now, if I knew that C was equal to 1, then I would not have a general solution, I would have a particular solution. Right now I have a general solution. This is the best that I have. I need more information to go from general solution to particular solution. Let me now read this theorem. So capital F, there it is, that is the antiderivative of f. Now f is the derivative on an interval I. So if f is the antiderivative on some interval I, then g is an antiderivative of f on the interval I if and only if, here it is, g of x is equal to f of x plus c for all x in that interval, and c is a constant. So what I want to do is I want to go ahead and rewrite this integral of, my apologies here, the integral of f of x. Look at me, I can't even write. Okay. So the integral of f of x with respect to x is equal to capital F of x plus c. And all I'm going to do right now is just give each part a name. Okay? So this, again, this elongated s is our integral sign. Okay? And it does mean sum, and as in adding, but I don't want, we'll come back to that later. The lowercase f of x, now that is the derivative, but we call it the integrand because that's what's inside the integral. Just like when you have the square root of x, the x is the radicand, right? And the radical is the square root. So f of x is the integrand. The dx is the variable of integration. You can't, just like when you take a derivative, you have to take a derivative with respect to something. If you're going to integrate, you have to integrate with respect to a variable. Okay, over here, capital F of x, right? This is an antiderivative. It's an antiderivative of f of x. And finally, the c is what we call the constant of integration. The constant of integration. Okay, so far so good. So where do we go from here? Well, just like you are just starting to get pretty good with a lot of those differential formulas, now you're going to have some more formulas, and this is not exhaustive by any means. But the good news is for now, the one that we're going to focus on is this guy right here, the power rule of integration. So let me write that a little bit larger, right? And that power rule of integration looks like this. So we're going to, if you want to integrate x to the power of n, I'll tell you what I'm going to do is I'm going to write this, by the way, that's a highlighter. I'm going to write this big enough that I can copy and paste it as I go from page to page. Ready? So if you want to integrate x to the n with respect to x, you can do that by, well, let's think here. Don't write this. I just want to help you think here. When you would take the derivative of, let's actually just make this easy. Let's make it x squared. When you took the derivative of x squared, didn't you subtract 1 from the exponent? Right? So wouldn't it make sense if you're trying to do the inverse operation that we would add 1? So this is going to be x to the power of now plus 1, so n plus 1, over n plus 1. Now that over n plus 1 will become apparent in just a second. Plus c. Do not forget plus c, even if I forget plus c. Don't do it. I'll have to take off points. Now there is a caveat here. This is a caveat that we will not be able to address right now. But this assumes that n does not equal -1. Okay, you can see it right now. If n is equal to -1, you're dividing by 0, right? So let me go ahead and take a screenshot of this guy so I can carry it along for the ride. We'll save the image. All right. So ready? Let's now let's go ahead and answer this question. So we'll come back and we will refer to some of these integration formulas as we need them. I am going to, you know what? I'm going to crop this. I don't want they're already telling you how to start. So what we want to do is we want to find the antiderivative, or you'll hear me find the antiderivative of the following derivative, or you might hear me say just simply integrate. These are two different ways of me asking you to do the same thing. Okay, so the directions are find the antiderivative, or the directions are integrate the following, either one. So how do we approach this? Well, let's go ahead and use this power rule. In fact, since it's the only rule that you're going to be practicing for this entire section, everything that I put in front of you, you should think that, okay, somehow I can use this rule. So, all right, so this is the first problem, so let's take our time. Let me rewrite it. So we want to integrate 3x with respect to x. Okay, now this is an optional step. You don't have to do this. But I think you'll find that most of the time it's easier to bring the constants out in front of the integration symbol. So notice, I can always take any constant and bring it out front of the integral. You can do the same thing with a derivative, right? You have seen me do that before. So really, this is our question. And I'm going to go ahead and put since this is x to the power of 1, I'm going to go ahead and show the 1. And now let's start to use this formula. So to integrate that, it should be x to the power of n plus 1 over n plus 1 plus c. So let's go ahead. So in this case, n is obviously equal to 1. So let's start to apply this formula. So this is going to be 3 times, don't forget your 3, x to the power of 1 plus 1 over 1 plus 1 plus c. All right, so I can erase this now that I have the formula saved to a screenshot. And now let's just clean this up. So this is going to be 3 multiplied by what? X squared over 2 plus c, which is basically 3 halves x squared plus c. It's okay if you want to write that as 3x squared over 2 plus c. That part doesn't bother me. Again, I think you'll find that if you just think about division as in terms of multiplication, right? So instead of dividing by 2, multiply by half. I think you'll find that your work is a lot easier. But I'll leave that up to you. All I'll do for the rest, we're going to go ahead and stop this video and start back up soon. All I'll say is, look, when this integration symbol disappears, this plus c should appear. And that's all I'll say. Does it make sense to you that the good news is, right? So this is your proposed solution for the antiderivative, 3 halves x squared plus c. It should comfort you to know that you can always check this work by doing what? By taking the derivative. What is 2 times 3 halves? Well, that's 3. So you end up with, and what's the derivative? So we end up with 3x plus 0, right? Because the derivative of c is 0. So it should comfort you that you can always check your work by just taking a derivative. All right, that's part A. I will see you for part B soon.